I now have the privilege to welcome our first panel of 2022 new fellows to the stage to discuss mitigating climate change. The moderator for this session is Dr. Alex Swanhass, our Energy Co-Advisory Board member. And joining Alex on the panel, if I can start to introduce our new fellows, Professor Kylie Catchpole, Deputy Director, School of Engineering, Australian National University. Professor Kylie is a global expert in solar energy. Her pioneering work demonstrating new approaches to increase the efficiency of solar cells and solar hydrogen technology has shaped the field. Professor Xiao Hao, School of Photovoltaic and Renewable Energy, UNSW. She's a world expert in solar technology and has helped establish Australia's global leadership in this field. We've got Professor Mark Howden, Director of Australian National University's Institute for Climate, Energy and Disaster Solutions. Professor Mark Howden is an international force in climate change science. He's been a member of an extraordinary 20 intergovernmental panel on climate change processes since 1991, sharing the 2007 Nobel Peace Prize with other IPCC participants and Al Gore. And finally, Dr. Elizabeth Ebert, Senior Principal Research Scientist and Head Forecast Quality Research at the Bureau of Meteorology. Dr. Elizabeth is a meteorologist with extensive experience working in governments, and she holds science leadership roles in the World Meteorological Organization and has considerable influence on international research in impact weather. Please join with me in welcoming the first panel to the stage.
Good morning, everyone. There's probably no better topic to start these panel discussions than mitigating climate change. Climate change is arguably one of the biggest societal, economic, political, and technological challenges of the 21st century. And at its core, climate change has actually been caused in part by technology, but technology also offers the cure for it, but it needs to be technology that is going to be adopted by society. And that will be one of the themes today, and it's obviously one of the themes of Activate. It is also a very urgent problem to solve. In fact, it should have been solved last century, but frankly, we have fiddled for too long. Now is the time to act. And I think what we'll hear from the panel today is there is hope, there is a lot of action, but there's frankly also a lot to do. So the way we are going to run this, each of the new fellow panelists will provide a short introduction. I'll ask them a couple of questions, but then it's really important that you actually think about your questions and ask those questions. I think there is an app where you can enter your questions, and we have a screen, and technology will obviously work beautifully, and then we will pass on at least some of the questions to the panel. So without much further ado, maybe I'll just start with you. Kylie, do you want to provide a quick introductory statement?
Sure. So energy is responsible for over 70% of greenhouse gas emissions. So getting to net zero means we have to completely transform our energy system. This is recognised by the International Energy Agency in 2021. It's hard to overstate the scale of the transition that's required. This transition is going to be the biggest change in the way we generate and use energy since the Industrial Revolution. Solar has a big part to play in this transition. So at the moment, 40% of the new electricity capacity that we're installing globally each year is solar. In second place is wind. So we're already transforming the energy system, and this is because solar and wind are cheaper than the alternatives. At the same time, we're going to be decarbonising heat by using electricity. We're also going to be transitioning to electric vehicles. The other part, of course, is other sectors that are hard to decarbonise, and here's where sectors like hydrogen are going to play a big part in high temperature heat and heavy freight. I want to touch on one other thing that Alex mentioned, and the idea of hope. Optimism is really important here. So this is the part of the system as well that's a part of the socio-technological system. There's a nice story here about the Paris Climate Agreement, actually. So Christiana Figueres was the lead negotiator of the 2015 Paris Climate Agreement. And when she took up her position, she was asked whether she thought there could ever be a global agreement on climate change. And she said, "Not in my lifetime." She said that publicly. And when she said that, she realised that if she didn't think there could be a global agreement, then no one thought that there could be a global agreement. So she recognised that her first task was to actually help other people believe that it was possible to make the transition. And you can see that that was wildly successful. It's completely changed the way the world approaches climate change. So that's one thing I've taken on in my teaching. There's a tremendous amount of anxiety around climate change among young people these days. So we need to address that as well. We need to empower young people. And so in my teaching, I've been teaching a new course called Optimism and Agency in Times of Change. And it aims to help young people find a positive difference that they can make in the world and actually go ahead and make that change.
Thank you, Kylie. Very inspiring. Xiaojing.
Thanks, Alex. Definitely I agree with Kelly. So the climate change actually is a global emergency affecting every one of us and also our next generation. So actually, energy is at the heart of this climate challenge. So, but also going to be the key to the solution. So to mitigate this climate challenge, we also definitely need to reduce the reliance on the fossil fuel and also accelerate the transition to using the renewable energy sources that are clean, accessible, affordable, and also sustainable in the long way. So in the solar field, what we are doing, we continuously driving down the cost of the solar module to make it cheaper, and also to improving the energy conversion efficiency to get more power output from the unit area. And also we are using green and also cheaper material to make it long-term sustainable. And also we're trying to make it more flexible and also more widely deployable. So if we're looking at what happened now, so the transition to the zero emission is actually happening in all the different fields, and particularly for the fields which are actually greenhouse gas emission contributor largely. For example, energy intensive industry, and also the building and the vehicle and etc. So I think the pathway is going to be through multidisciplinary collaboration. It's not just one field going to do, because we know the challenges for each field for this transition is going to be different. So I think the collaboration and also the multidisciplinary communication is greatly important. For our case, like I'm working on thin film solar cells, basically it's coating the thin film on different type of surfaces. For example, glass, steel, and also like stacking on silicon to make it more efficient. But also I think another mission, what I need to do is, and also our work is working on to get more engaged with different industry, to trying to understand their needs and also their challenges to this transition so we can cope with this climate change together. Thank you.
Thank you. So I come from the Bureau of Meteorology, which most of you would know is an information providing organization. And with our partners in CSIRO and universities, we do a lot of climate science. And so we're about providing information that people need to make informed decisions about mitigation, about adaptation, and about staying safe as well. And so we know that the climate is already changing in Australia. In the last century, it's warmed by about 1.4 degrees in Australia, which is astonishing. And so the past is no longer a good guide for what we can expect now, much less in the future. And so this information that about the changing climate and what it means at a local level is needed at a lot of time scales, from tactical, there's a threat that's imminent and we need to respond, to strategic, planning resources, thinking about staffing up and preparedness, and onto planning timescales where you might have structural solutions like dams and also policy changes. So information is needed across all of those scales. So I wanted to just mention two things that are going on that are contributing to the information. So first is something that's called climate attribution, and that's a way of understanding how much of what we're observing with conditions or maybe an extreme event could you put down to climate change versus it just happening anyway. And so the science is quite a new science. It's been around for no more than 20 years, but it's really growing rapidly. And we have a lot of great climate scientists in Australia who are working in this space. And the idea is to compare what's happening, say an event that's looming or an event that's just happened, under our changing climate to what might have happened if there hadn't been increased carbon dioxide and global warming associated with that. And you can there's a few mathematical methods that you can use to do that. One of the things that the Bureau of Meteorology is trying to move into is real-time climate attribution, where if we look in our seasonal climate outlooks and we see wet month ahead or fires more likely or whatever, we can do those experiments of the no climate change situation against what's in the forecast and try and attribute how much of that is due to normal climate variability like El Nino and other things versus climate change. And that makes it really compelling as a communication device to help people understand what's going on. The other thing I'd like to mention is the Australian Climate Service, which is a brand new initiative of the Australian government, started last year. Again, partnership between the Bureau of Meteorology, CSIRO, Geoscience Australia, and the Bureau of Statistics. And the idea with the Australian Climate Service is to provide up-to-date climate information all the time, so about what's happening now and particularly hazards and impacts. Before, we've had major climate updates every, 6 to 8 years or something. We're now trying to move this into continuous updates and a whole variety of service to our emergency management agencies, to governments, and to other partners so that they'll be able to anticipate what to expect now and in the future that's associated with our climate. Thank you.
Thank you, Beth. Mark? Thanks, Alex, and thanks to ATSE for the opportunity to be here. When we look at what's actually going on in the world, is that in spite of the fact that Christiana Figueres had some hope about a global agreement, and most countries signing up to that global agreement at Paris, we have continued to increase our greenhouse gas emissions. Last year, they were at record levels, and our atmospheric concentrations have gone up accordingly. And that's understood. We understand the science behind that. And when we look at the science, it's actually very, very clear that we not only have to go to net zero to meet the Paris Agreement temperature goals, we have to go below zero. And that below zero, I think, is a unique opportunity for science and technology to step up. It's not just the fact that we have to reconfigure our energy systems, we have to do a lot more than that. And so when we actually start to think about this, it actually means we need systems solutions. We actually need whole of system solutions, not partial ones. And at the moment, we tend to operate in partial solutions. And that means we not only have to have the technology and the engineering components, but we also have to bring in the social science and the political science, psychology, social psychology, and various other things. And so we need, I think, to have a much more comprehensive approach than we've historically taken. And again, that I think is a really significant opportunity for ATSE. So along the lines of thinking about system solutions, because that's how I sort of operate, is that within the climate change domain, I've actually deliberately gone out and developed capacity in the climate science domain, in the impacts and adaptation domain, in terms of emission reductions in various sectors, and also in the greenhouse gas inventories, because we need evaluation tools to see how well we're going and are able to adjust our course. And as well as that, I've actually worked deliberately again in terms of science policy, so we have capacity to deliver science into policy, and also with communities. So we actually have the value statements of communities that actually drive change as part of our tool set. And so from my perspective, we need to have all of that, but we also need to wrap around this a principled approach to science and technology which brings in ethics and values as part of our core operating principles, so that we actually know that we're doing the right thing. So when we actually start to sort of take apart a little bit of the greenhouse gas emission reduction challenge ahead of us, is that I think we can sort of reconfigure some of the conversations a little bit. And that is just simply recognising greenhouse gas emissions arise from demands for goods and services. That's the ultimate origins of each individual greenhouse gas emission. And so the big challenge ahead of us is how we can deliver those goods and services with a much lower footprint, greenhouse gas footprint and broader environmental footprint, and deliver social and other benefits at the same time. That's a systems approach, that's a comprehensive approach. We're a long way from that at the moment. So if we actually think about this, probably the first port of call in terms of reducing emissions and achieving that footprint goal is looking at efficiencies. And efficiencies tend not to be very sexy. They're not, new high-tech stuff. They're often just managing existing systems better. But that's what engineers do incredibly well. There's a huge role there. Secondly, we need to look at new technologies. So we haven't got all the toolkits in our toolbox at the moment, or tools in our toolbox, to do what we need to do. So we need new technologies, but we also need whole-of-systems approaches so that we can actually deliver those technologies effectively. And at the moment, I don't think we have those. So we need to be able to lead discussions about how we need to evolve as a society in terms of our use of resources and our relationships with each other. And we need to actually be prepared to engage in that debate in a very honest and transparent way so that we actually can combine those ethics that we have and actually deliver those in a comprehensive systems package.
Wonderful. Thank you, Mark. So maybe let's start off with actually unpacking this topic of climate change itself a little bit more. Climate change is a very unfortunate and confronting reality that we're living in. One of the consequences of it is increased frequency and severity of extreme events. And if we needed any more proof or attribution, we have seen just this week that flooding events again broke records. So Beth, your work at the Bureau really focuses on better understanding and managing extreme events. Can you give us a bit of an overview of what is actually the latest evidence on observations of extreme events and where are we going to head to?
Yeah, thank you. So there has been a lot of recent evidence where we're experiencing it. So if you have lived in Sydney, you've seen all of the flooding over the last couple of years. We know that rain rates are getting stronger, so flash flooding is more of a risk. And you've heard the phrase, the climate on steroids. That's a kind of a nice throwaway phrase, but what's going on then is that the warmer climate holds more water vapor, and that supports more active convection. And so all of the things that you have to worry about with flash floods, and the storminess as well. So all of those things are increasing in intensity, perhaps not in frequency, but what is increasing in frequency and intensity as well are heat waves and fire seasons. And I think this is something that we really need to be very concerned about. Heat waves are getting hotter, they're getting more frequent, they're getting deadlier, and fire seasons are getting longer, they're getting also more deadly. And with the Black Summer a couple of years ago, one of the things that we observed that year was the preponderance of these fire-induced thunderstorms, where the heat of the fire creates its own storm. There's pyrocumulonimbus is the official name for that. But there were many, many of those observed that year, where before there had been just the odd one here or there. And those are incredibly dangerous local things for people who are fighting the fire or might be in the way of the fire. So that's just an indicator of some of the ramped up things that we're seeing.
So how can we better forecast these events? I mean, that has become very apparent, for instance, also in the flood season. That probably requires investment of financial resources, but it probably also requires new scientific approaches.
Yes, you're right about that. There's a lot that we don't understand about the mechanism, so there's a lot of basic science that is still needing to be done, and we're relying on our universities to do a lot of that work. Observing systems are incredibly important, and I'm very encouraged by the Australian Space Agency and moving more seriously into remote sensing, because we know that on a big country like Australia, we rely a lot on what we can observe from space. So that's in the observations. Modeling, numerical modeling is just the linchpin of all of our predictions, and those are being improved through partnerships. But beyond that, and the ATSE NRI, very important, which is the ATSE is our national weather and climate model. But we need to apply statistical methods as well. So, and this is where I think there's a huge potential for machine learning, not to replace weather models, but to enhance them and post-process the outputs of those to try and link them better to the impacts and what people feel on the ground. So I think that would be something I'd love to see a lot more of. And then importantly, and Mark has alluded to this, the role of people and trying to understand how people behave, how they act, how they understand things, and making sure that anything that we can predict is well communicated and well understood so that people are able to take appropriate action.
Thank you very much, Beth. So climate change is real. What can we actually do about it? And that's what we want to unpack in the rest of the session. And Carly, you refer to it. Energy is obviously one of the key contributors. Sort of electricity and stationary energy make up about 53% of Australian emissions, and even more if you include transport into it. There's a lot of technologies out there, and there's actually, on the theme of hope, a lot of things we can be hopeful and frankly proud of. When you look at Australia, there's actually some great work being done by Andy Blakers and a number of his colleagues at the ANU that looked at renewable energy adoption on a per capita basis on planet Earth. And what most people don't know is Australia is actually leading the world in the adoption of renewable energy. And it's not just by a small margin, it's by a large margin. We are also featuring one of the highest rooftop PV penetrations in the world. That causes its own challenges, and maybe Marion York, another new fellow, has to deal with those things on a day-to-day basis. But we also have, frankly, some of the best researchers in the world in the field of renewable energy. And it's a great pleasure to have both Carly and Xiaojing on the panel, who both in sort of different cell types actually have held world records in cell efficiency. So congratulations and thank you for that. Xiaojing, I might start with you. So we have driven cell efficiency to really very high levels. How can we drive cell efficiency even further?
Okay, I think that's a very good question. But the first thing, before I answer that question, I just want to clarify one thing. So a lot of, we set up, say, we're doing for the higher efficiency. Higher efficiency is one of the major solutions to further driving down the cost of the solar module. But another important thing is, look at like the integration of the solar cell with the different applications. For example, BIPV and a solar powered vehicle, and even like a solar agro. And even we think about like a solar farm. So when we have the limited space, we can put on a solar module. So one of the important things is we get more electricity from unit area. So that's, I think, another key point for driving efficiency. So the solution to driving the cell efficiency, we know like silicon has already been very efficient, but it's not enough. So we do have the solution to further drive the efficiency even higher. So one of the solutions, there are a lot of advanced concepts, for example, like the hot carrier and also tandem cells. But in the solar PV field, we all agree tandem solar cell is going to be one of the most feasible and promising solutions to further drive the efficiency of the solar module. So tandem solar cell, the concept is you stacking the solar cell made from the different material. They have different band gap together, so each cell going to be converted getting the electrical current from the different wavelength range of the solar spectrum by their best response. In this way, actually, they can most efficiently convert the sunlight in a much broader solar spectrum to the higher, much higher electricity and also the higher efficiency. So when we say that, the concept actually is not new. So probably if we look at it, what happened now, actually the tandem solar cell made from the 3-5 materials like gallium arsenide, those group, actually has been widely used to power our spacecraft. However, I think like the highest efficiency by the 3-5, the two cell one, they can have the efficiency 35%. And when you stack it more, and I think the highest one so far is already more than 45%. So that's a very good pass. However, so far it's only limited in the application in the space, aerospace. The reason for that one is it's still too expensive. When we come to the terrestrial application, it's really hard to compete with silicon because it's too expensive. So what we are doing, what we are trying to do is we're trying to figure out like the better solution by using a similar tandem cell concept, but we can really get something cheap which can be used on the planet. Not in addition to the space. So by saying that, so there are a lot of different combinations of like a top cell and the bottom cell for the tandem cells. But so far, given the like dominance of a silicon PV module, like it's accounting for 95% of a PV market. So the really like a most important and most promising way is actually silicon-based tandem solar cell. So which one is better to put on the silicon? So far, there's still a lot of argument in the PV field. So I think from our point of view, we keep our mind open. So we're looking at different alternatives. So like so far, the good one is the 3.5 and some chalcogenide, and also you might have heard of like a perovskite as well. But for each these top cell, they all have their own scientific problems. Some are related to the cost, too expensive. Some are related to the efficiency, not high enough. Some are related to the stability, like cannot last long. So we are working hard and keep it open to all of these kind of alternatives and trying to drive this kind of scientific breakthrough and then the efficiency breakthrough. But definitely like these are, I think, so far the most promising solution for this one. So I think the answer is yes, we can further drive the efficiency and also we are on the way to do it.
Well, that is great news. Thank you, Xiaojing. I think what you have highlighted is the cost of solar is not only low already, but it will further decline. So we've really, I think, solved the question of how do you produce energy cheaply. But there's still another big question outstanding, which is how do we actually store this energy cost effectively and make it available when we need it? I mean, batteries, which is a probably discussion in itself, are fantastic in doing this for short duration. But the real outstanding question is how do we do this for long duration? So Carly, you are multi-talented. Not only have you developed new cell technologies, but you've also started to do a lot of work in the amazing topic of hydrogen. So how do we bring down the cost of hydrogen and really get to that magic $2 a kilogram to solve that outstanding challenge?
So it's an interesting question. I would slightly disagree with you, Alex, about whether we've reduced the cost enough.
We always say more.
There's 2 points, I suppose. One is that solar energy will be our dominant energy technology for the world. So we should keep researching it. We should keep bringing down the cost. So that's one point. The other point is for hydrogen, we need to keep bringing down the cost, not just for storage, but for anything that you might want to use hydrogen for. So you can use hydrogen for a number of things. You can convert electricity to hydrogen and then back to electricity, for example. In that case, it's acting as storage, or you can use the hydrogen directly. You can burn it. You can use it to reduce coal to make steel. So lots of different applications. For all of those applications, it's still much too expensive. We should not be concerned about that in the longer term because, I mean, when Gina and I started our careers, solar was much too expensive. Right, so if you keep the technology development, if you keep the installations, we can reduce the cost. We can certainly do that. What do we need to do? Well, half the cost of generating hydrogen from renewable electricity is actually the electricity itself. So for that reason, we need to keep reducing the cost of renewable electricity because doing so in itself is going to reduce the cost of renewable hydrogen. The International Technology Roadmap for Photovoltaics expects us to reduce the cost of photovoltaics energy by around 40% in the next 10 years. So we could go faster if we develop the technology faster, if we increase the deployment, but that's already a very significant factor. To reduce the cost of hydrogen more, though, we need to do more things. We need to start actually installing hydrogen in the same way that we did for photovoltaics, also for wind. Once you start installing, then you can reduce the cost by economies of scale. And until you do that, you can't actually reduce the costs. So that's super important to find those initial markets for hydrogen. And there's some areas that look prospective at the moment, for example, generating hydrogen and using it to produce ammonia, which you could then sell. That seems already like a prospective area. So we should look for those areas where you can already start to install them. And the other thing that's not really talked about much in hydrogen is storage. Storage for hydrogen is cheap if you happen to have a handy underground salt cavern. If you don't have one of those available, then it's not necessarily cheap. Compressed hydrogen is pretty cheap, but it's bulky and you can't transport it long distances. And the other ways that you can store large amounts and transport long distances are not that cheap. So there's a lot of work to be done there as well.
Thank you, Kylie. So I think we've made some progress, but as you've rightly highlighted, there is a lot more work to do, including but not limited to solar research. Before I get to Mark, I just wanted to highlight there is actually this link where you can enter your questions. I haven't actually seen any questions yet, so you will have the opportunity to ask questions in a minute, so take that opportunity. But Mark, transitioning to you. So we spoke about energy, lots of progress, a lot more to be done. What about the remaining 47% of greenhouse gas emissions? What are the priorities that we need to focus on there, including but certainly not limited, for example, in the agricultural sector?
Yeah, so if I sort of was a visitor from another planet and came down to Earth and looked at the media coverage and the political debate, I'd actually think that the whole issue is around electricity and renewable electricity. So 98% or something of the coverage and discourse is on moving from fossil fuel-based electricity production to renewables. And yet fossil fuels electricity production is around about 30% of our emissions profile, 70% is all the rest of the stuff. So in that 70%, there's a lot of opportunities, and so we need to be focusing on that 70%. Of course, that includes other energy-consuming sort of elements like industry, etc. So that's a point. We actually are missing the biggest part of the picture here, the biggest part of the opportunity space, because of the nature of the debate to date. If we sort of look at other systems, so taking some of what Kylie just said, hydrogen and storage, of course we need to think about other forms of storage, and batteries are a really big part of that. And clearly one of the technologies we need to accelerate is the energy density of our battery systems or storage systems. And so if we can actually increase those significantly, we can solve a lot of the other problems as well. And of course there's a price element there. There's technology options in terms of alternative fuels, so what we call e-fuels, where you use renewable energy to create essentially a substitute for fossil fuels. So this is a drop-in fuel alternative. And of course that just then cycles the carbon in and out of the atmosphere. It doesn't actually get rid of it, but at least you're not digging up fossil fuels and adding to the atmospheric burden. If we look at other sectors such as agriculture, which is quite a significant contributor, so food and agriculture across the globe, and here in Australia, 25 to 30% of our emissions, and yet we tend to ignore that component of emissions. And yet it's far too big to ignore, so it's roughly the same size as our electricity emissions. And so we need to have solutions to things like livestock methane. The things that are on the table now at best are partial solutions, and some of them actually have considerable disbenefits associated with them. So we need to be cautious and very reflective about how we approach those. But sitting amongst other sectors, so industry and industrial uses, there's lots of opportunities to reduce emissions through efficiencies. If we look at landfills and waste, more effective methane capture, better designed biodigesters, so that when we have food collection in our suburban bins, we can actually take that food and use it effectively, including through biogas digestion. And so a good opportunity for improved engineering there. And so when, and lastly, in terms of agriculture, is actually using our landscapes better, so we can actually store more carbon on those landscapes, which is actually a lot harder to do than people make out. But also at the same time actually generate other benefits, so biodiversity benefits, water quality benefits, etc. And so there's a lot of approaches that we can take to reduce emissions, but again, go back to my original statement, is we actually need to have a systems view of this, and we actually need to take a comprehensive view of all of the different benefits, costs, and pathways to actually delivering those.
Thank you, Mark. I think in your introduction you mentioned we have to go beyond net zero, and we have to go actually negative on emissions. Does this mean we have to do more on carbon capture and storage?
Well, thanks, Alex, for that doozy. So a lot of the attention so far has focused on carbon capture and storage, which people frame as capturing carbon dioxide, say, from the chimney of a coal-fired power station and then pumping it underground. So that is what people usually talk about. Basically, in spite of billions of dollars investment, that's a failed technology. Virtually every example of that across the globe has failed. The ones which are viable are what's called enhanced oil recovery. So you pump the carbon dioxide underground to push out more oil at the far end, and that actually makes climate change worse. So it's actually not a solution to climate change. So we need to move past that, and we need to be very straightforward in terms of our evaluations of the appropriateness of that as a technology. There are other carbon capture systems which probably make more sense. So, for example, in Iceland, Climeworks has got a direct air capture system which captures carbon dioxide directly from the atmosphere, and then it puts it underground to actually lock it up in the crystal matrix of the geology in that place. It's very expensive, but it is actually manageable. We have the technology to do it. It's just not at a price point which is easy to deliver right across the systems. So there's various people in Australia who are trying to prosecute that, what we call the negative emissions agenda. Sometimes it's carbon dioxide removal. So, for example, Diana Alessandro from Sydney University has got a sort of a stall outside, so you can go and talk with Deanna about this as well. But there's a whole range of different possible negative emissions technologies, many of which actually potentially make a lot of economic sense. And again, they're absolutely ripe for the picking. If we go back 6 years, if we'd actually moved on this in Australia, we'd actually be making lots and lots of money right now, and we'd be right at the cutting edge. We've actually missed that opportunity to be at the cutting edge, but there's still lots of opportunity there.
Thank you very much. So I'm now coming to questions on the audience. There's actually a lot. It was just operator error that I didn't see them, but I've worked it out, so I'm mastering the technology. There's fantastic questions. We are unfortunately not getting through all, but I'll start with one which sort of covers a new topic, and it's from Sally MacArthur. And the question is, we currently have a limited manufacturing sector for renewable energy technology in Australia, but can you comment on the opportunities or needs for the local recycling, reuse, repair industry and future for onshore manufacturing?
Yeah, I think that's a very good question. And particularly we cover, if we look at the solar farm now, I think one of the most important part is going to recycling after its end of use. I think that's definitely one of the part. And we know our colleagues at UNSW, we have colleagues working on this part, and also in addition to the process, but also in terms of the whole equipment design. So we are working on it. But I think in addition to that one, in the emerging thin film solar cell, and particularly for the tandem solar cell field, we also have some opportunities as well. So, in particular for some emerging thin film solar cell. So, from our base, one part is we are continue working on driving the efficiency. But we all know, in terms of manufacturing and keeping that efficiency and keeping the inline production reliability, design of the equipment based on our recipe is another important part. So what we are doing actually is based on our recipe, based on our experience, we are also working on design this kind of equipment. So we are looking for the opportunities to establish the local manufacturing for our next generation PV technology. So that's what we are working on. So I think we, particularly for silicon technology, I think particularly for the PERC, we know we got that technology invented here. But I think now we are trying to grasp the opportunity for the future PV manufacturing through the renewable, through the emerging PV technology, and also through the next generation tandem solar cell technology. I think that's a very good question. So we are looking for those opportunities here.
Great. Anything else to add on manufacturing? No? Okay, I have a question from Catherine Woodthorpe, and that's for you, Carly, and it's about ammonia. Mm-hmm. Is that actually a potentially more viable option for storing and transporting energy compared to hydrogen?
So it is an option for storing and transporting energy. You can convert hydrogen to ammonia. It is possible to convert it back to hydrogen. There are a couple of issues there. One, the converting back to hydrogen is quite expensive. And secondly, if you use it in fuel cells, then they really don't like the nitrogen. So there's issues there. But the converting to ammonia and then using it for ammonia, that's a market in itself. And so that would help hydrogen technology grow. So I think that's the near-term market. In terms of whether you can do it in the long term, there are a number of things that I guess that have to reduce in cost. So if you are able to do that, it might become viable there.
Excellent. Mark?
And one of the alternative uses, of course, is for use in fertilisers, and that's, I think, what Carla was referring to. And so, that's, I think, a really important area. So rather than using natural gas as your feedstock for producing nitrogenous fertilisers, we actually go to a hydrogen economy.
Fantastic. I think we've probably reached the end of time. I get a nod, which is really sad because there's so many good questions here. But you can obviously speak to all of the panel members in the breaks and hopefully ask your questions. But can I just thank you for a really fascinating unpacking of a very complicated topic. And I really love the theme of hope coming out of this. I think we can be proud of what we have achieved, but we need to recognize there is so much more to do. We need to do it quickly, and it's not going to be easy. But I think with the caliber of talent that we have in this country, I'm actually very confident we can achieve this. So, thank you.
Thank you.